Hey everybody, in this video I'll be going over empirical formulas and molecular formulas. I'm going to do two different problems. In the first problem I'll be solving for an empirical formula, and in the second we'll be solving for both a molecular and empirical formula. Let's go ahead and get started. Phosphoric acid is a common flavoring agent in soda. If 31.61% is phosphorus, 30.09% is hydrogen, and 65.31% oxygen, what is the empirical formula? So I'm going to underline just some key things here. Empirical formula, right? That's what we're asked for. And we know that we have three different elements: phosphorus, hydrogen, and oxygen in this specific chemical compound, right? And we're given the percentages of each of these. We know that this chemical compound consists of 31.61% phosphorus, 3.09% hydrogen, and 65.31% oxygen. So since we know the percentages, and actually if you were to add each of these up, if you were to add up 31.61 plus 3.09 plus 65.31, you do get something around 100%. So we know that these three elements are essentially the three components of this chemical compound. Now, since we know the percentages of these, the percent composition of each of these elements in this chemical compound, we can essentially assume, so we're going to assume that we have a sample. Let me write this smaller actually. We're going to assume a sample of 100 grams. So if I have a sample of 100 grams, how many grams of phosphorus do I have? Well, if I have 31.61% of phosphorus, I essentially have 31.61 grams of phosphorus. If I have that same 100 gram sample and I have 3.09% hydrogen in that sample, 3.09% of hydrogen in that sample would be 3.09 grams of hydrogen. And now oxygen is the final element. If I have a 100 gram sample, and in that 100 gram sample I have 65.31% oxygen, I have 65.31 grams of oxygen, right? So that's the first step that you need to do when you're solving for this problem, is assume that you have a 100 gram sample, and from that assumption, essentially calculate the number of grams of each element you'd have, assuming that you have a 100 gram sample. Now that we pretty much did the first initial step, we essentially have to convert each of these to moles. So we have to convert 31.61 grams of phosphorus to moles of phosphorus. Now the molar mass of phosphorus is actually 30.09. So for 30.09 grams, you get 1 mole of phosphorus. Now moving on to hydrogen, the molar mass of hydrogen is 1.01. Oh shoot. Let me use a different color here. The molar mass of hydrogen is 1.01, so you make that conversion from grams of hydrogen to moles of hydrogen. For every 1.01 grams, you have 1 mole of hydrogen. So convert each of these to moles, right? That's what we're doing. So for every 65.31 grams of oxygen, how many moles do we have? So we know, once again, that we are converting to 1 mole to moles of oxygen. So for every 1 mole of oxygen, we have 16.00 grams of oxygen, right? And I'm just going to put these in parentheses just so that you can see it more clearly. Now, when you solve for each of these, your answers should be these. You should be getting 1.02 moles of phosphorus, 3.06 moles of hydrogen, and 4.08 moles of oxygen. Now, this next step is going to be very important, and you want to make sure that you keep this in mind and you really just grasp onto this idea very, very well. We essentially have the number of moles of each element, right? Phosphorus, hydrogen, and oxygen in the chemical compound, right? Assuming that we have a 100-gram sample. Now, the next step is to divide each of these by the smallest number of moles. Now, of these three, which is the smallest? 1.02 moles, right? And that is for phosphorus. So we're going to divide each of these by 1.02. And I'm just going to write that. We're dividing by the smallest. We're dividing by the smallest, right? Let me box that in here. That's what we're doing here. So we are going to divide 1.02 moles of phosphorus. And since phosphorus is the smallest one, we divide this by 1.02 moles of phosphorus again. We're dividing 3.06 moles of hydrogen by 1.02 moles of phosphorus. And we are dividing 4.08 moles of oxygen by 1.02 moles of phosphorus. You're always going to divide each of the number of moles by the smallest one. It cannot be 3.06 moles in this case because 3.06 is bigger than 1.02, and 4.08 is also a larger number than 1.02, and so the smallest one is 1.02, obviously. And I really want to stress that you're always going to do it by the smallest number. Now, the next step is to divide each of these, and you should be getting this equals 1. This equals 2. And this equals 4. Sorry, let me fix this. This actually equals 3. And the final one equals 4. Now, remember, this was for phosphorus. The 3 is for hydrogen, right? Hydrogen. This one's for phosphorus. And the 4 is for oxygen. Now that we know this, we can write out our empirical formula, right? Let's draw a line here. Our empirical formula is going to be essentially H. How many H's do we have? 3. H3. How many P's do we have? You have 1 P in this case. So I'm just going to leave that subscript blank there. And then how many oxygens do we have? We have 4 oxygens, right? So it's going to be H3PO4. H3PO4 is our empirical formula in this case. And this is how you solve for an empirical formula. There's a lot of steps involved. You really have to keep track of all your work and be organized and neat. I hope you understood this video. I hope that after this one, you're able to really just calculate empirical formulas. Thank you very much for your time. And actually stay tuned. We're going to do one more problem. This next problem is actually a lot more complex. Not a lot more complex, but there are more steps involved. And so just keep track of all your work and listen very closely, right? An unknown molecule has a molecular mass of 60.1 grams per mole and has a composition of 13.4% hydrogen, 26.6% oxygen, and the remaining mass is due to carbon. What is the empirical formula and molecular formula of the unknown molecule? Now, in the last problem that I just went over, I essentially assumed that I had a 100-gram sample. I assumed that I had a 100-gram sample of the questioned or unknown molecule, right? Now, I was able to assume that I had a 100-gram sample because I essentially had the percent composition of each element in that sample. Now, in this particular problem, we have 3 elements that make up that mysterious molecule, right? They are hydrogen, they are oxygen, and carbon, right? And we know that from the problem because 13.4% of it is hydrogen, 26.6% is oxygen, and the remaining mass is essentially due to carbon. Now, the way that I want to approach this is like this. So if I know that 26.6% 26.6% of the compound is hydrogen. I know that, oh, sorry, let me fix that. It's not hydrogen. It's 13.4%. So 13.4% of this molecule is made up by hydrogen. 26.6% of this molecule is made up by oxygen, and the remaining percentage of this compound is made up by carbon. So I'll just put a little line here. Now 13.4 plus 26.6% equal to 40%. So these two elements make up 40% of the molecule. Now the remaining mass, remember, as it states here, the remaining mass is due to carbon. It's the same thing as saying the remaining percentage is due to carbon. So if 40% of the molecule is essentially due to hydrogen and oxygen, the remaining percentage is going to be just 4. It's actually 100 minus 40%, and your answer should be 60%. So 60% is the percent composition of carbon in this molecule. Now, this is important because once again, and I'm going to just leave the 60% there. This is important because if I'm approaching this problem just like I approached the last one, I'm assuming that I have a 100-gram sample, right? A 100-gram sample. And if I have a 100-gram sample of this particular molecule, it's the same as saying that I have 13.4 grams of hydrogen in this sample, right? 26.6 grams of oxygen in this sample. And it's also the same as saying that I have 60 grams of carbon in this sample. Now, if you got a little confused there, it's the same as saying that because since I know the percent composition of, remember, this one's due to carbon. If I know the percent composition of hydrogen is 13.4 in a 100-gram sample, 13.4% of 100 would be 13.4 grams here. If I know that the percent composition of oxygen is 26.6% of a 100-gram sample would be 26.6 grams. And once again, since we found out that 60% is a percent composition of carbon, 60% of a 100-gram sample would essentially be the equivalent to 60 grams. Now, let me get rid of all these lines I just drew, but that is just to show you how I came to obtain these values here. Now, what you want to do next is convert these. Remember, in the last problem, the step we did after we assumed that we had a 100-gram sample and that we essentially wrote out the number of grams that correspond to each element, assuming that we have a 100-gram sample. The next step was converting that number of grams to number of moles of that particular element. So we're going to convert hydrogen first. So if we want essentially we want moles of hydrogen up here. So for every 1 mole of hydrogen, how many grams do you have? You have essentially 1.01 grams of hydrogen. Let me make this a little longer here. This is for hydrogen. So for every 1.01 grams of hydrogen, you have 1 mole of hydrogen, right? Now for oxygen, you want moles of oxygen, right? We're converting to moles of, sorry, I made another mistake there. We're converting to moles of oxygen. Now, if we want 1 mole of oxygen, we have to convert from the molar mass of oxygen, and that is 16.00. So for every 16.00 grams of oxygen, you have 1 mole of oxygen. And finally, we have carbon. For every 12.01 grams of carbon, you have 1 mole of carbon. Now, the next step is just to calculate each of these, and remember our answer is going to be in moles, right? Because we are essentially just converting to moles. So the answer for carbon should be 5.00 moles of carbon. For hydrogen, you should be getting 13.26 moles of hydrogen. And for oxygen, you should be getting 1.66 moles. Now the next step is to analyze your three values. Next thing you want to do is just analyze the three values we have. And of these three values, which is the smallest? It's 1.66 moles of oxygen, right? 1.66 is smaller than 5 moles of carbon, and it's also smaller than 3.26 moles of hydrogen. So the next step is to essentially divide each of these by the smallest number of moles, which happens to be 1.66 moles of oxygen. 1.66 divided by 1.66 moles of oxygen, and then 5.00 divided by 1.66 moles of oxygen. When you divide each of these, you should be getting a whole number. You always want a whole number. Now for the top number here, I'm actually getting like 7.98. You just round that really to 8. So when you divide 13.26 divided by 1.66 moles of oxygen, just round this to 8. This one here is just going to be 1. This one here is going to be 3. Now that we obtain these answers, I want to work up here now. We're going to write out our empirical formula first, right? This is to solve for the empirical formula. I want to point that out. I'm not solving for the molecular formula yet. I'm solving solely for the empirical formula right now. Now, our formula is going to look something like this. CH, right? These are our three elements in the compound. We have carbon, hydrogen, and oxygen in this chemical molecule pretty much, right? Now, what are the subscripts though, right? That is what we were solving for, because we knew the three elements involved in this chemical compound from the start, but we didn't know what their subscripts were, and that is what we were doing. So the subscript for carbon is 3. Now, how do we know that? Remember, the 3 we obtained here was for carbon. The subscript for hydrogen is going to be 8. How do we know that? Remember, the 8 obtained here was for hydrogen, and the subscript for oxygen is 1. Now, whenever the subscript is 1, we just leave it like that. We leave it blank. We don't put a subscript. But it's 1 because remember, the 1 we obtained here was for oxygen. Now that we know this, just box it in. This is your empirical formula. Now, we are asked not only for the empirical formula, but also for the molecular formula of this unknown molecule. So this is the empirical. This is the empirical formula. But we're not done yet, because as I just mentioned, we're solving also for the molecular formula. Now, when you solve for the molecular formula, all you essentially do is this little division problem here. All that we do is essentially divide the molecular mass of our unknown molecule by the mass of our empirical formula. Now, in this case, the molecular mass is told to us here. An unknown molecule has a molecular mass of 60.1 grams per mole, right? So let's write that here. We have 60.1 grams. That's the molecular mass of our molecule. And the empirical formula, we have to know the empirical formula's mass. Now, in the last problem, I went over how to solve for, in the last video, I went over how to solve for the molar mass of an entire compound. Now, you should be able to do that. And if you're able to solve for the molar mass of the empirical formula here, once again, you should be getting something around 60.1 grams. So they're the same masses here. Now, it's not always going to be the same, but since it is the same here, you really just get 1. Now, what you're essentially supposed to do is multiply this answer by your entire empirical formula. So you should be doing like C3H8O1 essentially times this answer here times this answer here. But in this case, we just have 1. So our molecular formula is going to look something like this. It's really the same exact answer. As our empirical formula. So our empirical formula in this case is the same as our molecular formula, but this will not always be the case. Now, this is essentially how you solve for this empirical and molecular formula. I hope you understood how to do these after watching this video. I hope that you kept track of all your work and sort of just understood the details in this video. Thank you so much for your time. I hope you have a great rest of your day. Take care.